Welcome to Lecture 26, in which we will continue to talk about Toffoli Gates. But the first thing I want to do is to go back to Lecture 25 and correct a very small error that was made. Notice that here in the where we're talking about the Toffoli Gate for the first time, and we're over here writing out the output for various inputs. Remember how this works. The C on the output side will always be equal to C on the input side, except when A and B are both equal to 1. And in that case, when A and B are both equal to 1, as is stated right here, then C will be equal to C prime. However, if you look in this seventh line, in both the seventh line and the eighth line, A and B are both equal to 1. And so in both of these cases, the C output line should be C prime. So it's correct here, but right here, this should be C prime. So I'll correct this right now, C prime, and now that's correct. So again, the output C is always equal to the input C, except in these last two cases, because in both of those cases, A and B are both equal to 1, and so here where C is equal to 0, then C prime would be 1, and C is equal to 1, C prime would be 0. So just be aware of that, of that change. If you're keeping notes, go back and change that in your notes. So now we return to Lecture 26, and we have a very simple goal in this lecture, and that is to answer the question, how could we implement X ORed with Y using Toffoli Gates? And we're thinking now of X and Y being classical bits, and we want to use Toffoli Gates to implement X ORed with Y. And furthermore, we'd like to do it, since we're using Toffoli Gates, we expect that this implementation will be reversible. So how might we do this? Well, we learned in the last lecture that the Toffoli Gate can be used, if we have the right inputs, it can be used to calculate the NAND of two variables. What I mean, just to be specific here, we found that, so I'll say last time, we found that T of B1 B0 1 is equal to B1 B0, and then the last term will be B1 B0. B1 and B0 will be ANDed together and then complemented. And I guess I've been using prime for complement, so let me be consistent and use prime here. And this is given in your book as well. So this means effectively that if we want to NAND two Boolean variables together, we can use the Toffoli gate as long as we use those two Boolean variables as the control bits and set the final bit equal to 1. Then the final bit of the outcome will be the NAND of the two Boolean variables that we have. So now that we have a NAND gate, how does that help us? So I'll say, so we can NAND B1 and B0. Okay, so now the question is, so now we ask if we can write X ORed with Y in terms of operations with NAND gates. And the way that I like to do this is the following. Okay, we start out with X or Y, and I feel confident that all of you will agree that if I complement that 2 times, I get back the same thing. X or Y is the same thing as X or Y complemented and then complemented again. And this is the same thing as X or Y complemented and then complemented. Now I'm going to leave the outside complement where it is, but for the inside complement, I'm going to use De Morgan's theorem. Now, in case you haven't heard of De Morgan's theorems before, it goes like this. It says that the complement of a product is equal to the sum of the individual complements, and the complement of a sum is equal to the product of the individual complements. And if you've never seen this before, you can easily verify it by simply looking at the truth table. X can assume 2 values and Y can assume 2 values. So for this term on the left, you can have 4 possible combinations, 0, 0, 0, 1, 1, 0, and 1, 1. And check out in each case what you would get over here and what you would get over here, and you would find out that it'll be equal. And likewise, you can do the same thing here and here and find out that those two will be equal. So those are 2 of De Morgan's theorems, and they're frequently very helpful, and we're going to use them here. So for this inside expression, the complement of a sum is the product of the individual complements. So we have X prime, Y prime, prime. Now, why is this helpful to us? Well, we notice, looking at what at the expressions we have in the book, we notice that X prime is, well, let's see, how should I say this? I'll put it this way. T of 1, 1 X is equal to 1, 1 X prime. And likewise, of course, then t of 1, 1, y is equal to 1, 1, y prime. So this shows here how we could obtain the x prime and y prime using Toffoli Gates. But then once we get x prime and y prime, how do we negate that? Well, we could say we could use this same principle, t of 1, 1 x prime, y prime. Oh, wait. Here we go. X prime, y prime equals 1, 1 x prime, y prime. Prime. So by using this fact using the fact that t of 1, 1x is equal to 1, 1x prime, using this 3 different times with 3 different arguments, we are getting, in our third output here, we are getting x or y. Now let's see if this really does work. So to check this out, we will proceed as follows. Let's say that we have 1, 1, x, 1, 1, y, and let's see, wait just one moment here. Okay, let me make one change. What we have above is not incorrect, but it still begs the question of how do we get this x prime, y prime, how do we get that anded together? And of course we know that we can do that. That's one of our other identities for the Toffoli gate, is that t of x, y, 0 is x, comma, y, comma, x and y, but there's a more efficient way to do this. So let me erase this last one, because there's a more efficient way to approach this. If we now take the x prime that we have from the first calculation and the y prime from the second calculation, and have our third bit as 0, then we will get x prime, y prime, and x prime, y prime. Sorry, this 2 is right, but we can make this still better. Let's make this 1, and then we will get immediately, for the last term, x prime, y prime, prime, which is exactly what we want. So finally, now to review, we use this principle twice. T of 1, 1x is equal to 1, 1x prime. We use it there, and also we use it with y to get y prime. And then in this last expression, we'll use this identity to finally get the desired term here. So let's now see if this really does work. So we'll put 1 and x here. Let's see, somehow this has gotten, let's see. Okay, 1 and y, and then 1. Okay, and we'll draw a line for each one of these. Now the Toffoli gate then for 11X will be this. Here's the Toffoli gate to implement 11Y. And then finally, we want a Toffoli gate to take the outputs of those first two Toffoli gates, the third output of each, and use those as control bits. And then notice that here will be the controlled line, and it has a 1 on it. And I want to, what I'm claiming is that, well, we'll call this output here A, and we're hoping that that's going to be X ORed with Y, but we'll see. Now, I want to add one more part to this. Remember that we wanted to do this reversibly, and so I want to see what will happen if we now put all these same gates once again in the reverse order. Will it bring us back to where we started? So these will be our questions, and we'll just make a truth table now, X, Y, and A, and we'll see if if A is indeed equal to X ORed with Y. So we have 0, 0, 0, 1, 1, 0, 1, 1. Now, when we look at the first line of this circuit, we see that over here on the right, we will get a 1, because this 1 that comes in is never changed. And the same kind of thing happens for the second line. So we'll have 1 here. And the same thing happens for the fourth line and the fifth line, and these fourth and fifth line. We'll have 1 here and 1 here. None of those is ever changed. But on all the other lines, we do have X's, and so there will, under certain circumstances, be inversions. So let's now look more carefully and see what will happen. Well, on this third line, since it is being controlled by the first two lines, and both of them have 1s on them, we will definitely have an inversion occurring right here. So after this this first gate, we're going to have X prime here on this line, and we will continue to have X prime until we get to this point. Now, once again, these two lines have 1s, so this inverter will be operative, and that X prime will get inverted back to X and will not be changed again. So we have X here. Let's look at the line for Y. This line is being controlled by these two lines, which both have a 1. So the Y will definitely get inverted, and this will be Y prime here, and here, and here. What about when it comes to this inverter? Well, this inverter is controlled by these two lines, both of which have a 1 on them, so it will indeed be operative, and the Y prime will get inverted back to Y, and no more changes. So that is Y. And then finally, let's look at this 1 here. We want to know, okay, the way you can look at this one is the following. This 1 will stay a 1 unless there's a 1 here and a 1 here. in which case the 1 will get inverted to 0. But if there's a 1 there and a 1 there, then there is a 1 there and a 1 there, in which case the 1 would be inverted again here back to 0. So unless you have a 1 here and here, in which case you also have a 1 here and here, unless that is the case, the 1 goes all the way through unchanged, and if you have 1s at those 4 places, then the 1 will get inverted here, but then inverted back again. So either way, you conclude that this 1, on this line, the output will be 1. And so now by comparing the output lines with the input lines, we see that indeed everything here is reversible. So we have checked that part of it. This is a reversible circuit. And now the only remaining thing is to find out if this A here, which is the value on the final line between these two between these two Toffoli gates, is this value indeed X or Y? So let's see how to calculate that. Well, I think that the easiest way to calculate that is probably to reason as follows. Okay, and it's related to what we were just talking about. Notice that the value on this last line is going to be 1 everywhere, except in the case when these 4 values are equal to 1. And in that case, A will be equal to 0. So let's look at these 4 values and see what would force them to be equal to 1. Okay? Well, let's look first at this line. Now notice that we have X coming in here, and as we have already said, since we have a 1 on these 2 lines here, we will definitely have X prime here on this line. So right here, in these 2 spots that we identified of interest, we have X prime at both of those locations. And similarly down here for this line, we have Y coming in here, and these 2 lines have a 1, so we will definitely have Y prime here. So we have X prime here, X prime here, Y prime here, and Y prime here. And we've already said that A will always be equal to 1, except when we have a 1 in all 4 of those locations. And we will have a 1, and in that case, when we do have a 1 in all 4 of those locations, A will be equal to 0. So now we ask, what condition would make us have a 1 in all 4 locations? Well, we've just identified the top locations. The top 2 locations are both X prime, and the bottom 2 locations are both Y prime. So we want X prime and Y prime to both be equal to 1, which means we want X and Y to both be equal to 0. That is the condition. When X and Y are both equal to 0, then the X gets inverted here, the Y gets inverted here, so this would be 1 and 1, and so that would trigger this inverter here, and the 1 gets inverted to a 0, and A would be 0. So in the case when X and Y are both 0, when X and Y are both 0, then both of them are going to get inverted to 1s, and when both of these are 1s, this will invert this 1, and A will be 0. But otherwise, if either X is 1, or Y is 1, or both X and Y are 1, in any of the 3 remaining cases, at least one of these variables is equal to 1, so that when it gets inverted, at least one of them will be equal to 0, and if either one of these is 0, neither this inverter nor that inverter will be operative, and therefore A, this 1 down here on the last line will go all the way through, never disturbed, and A would be equal to 1. So in the last 3 cases, A is equal to 1. And now compare that to the truth table for X or Y. We can put one more column here. And of course, 0 ORed with 0 is 0, 0 ORed with 1 is 1, 1 ORed with 0 is 1, 1 ORed with 1 is 1, and so indeed A is equal to X ORed with Y. And this shows how we can reversibly implement the OR operation with Toffoli Gates. And that is all we'll do for this lecture, and now let's look at problem or two. Okay, so we'll just have one problem for this lecture, and then one or more for the in-class part. But the lecture problem will concern this circuit here. You can check this is a reversible circuit. You're not required to check that, but I'm saying that this is reversible. And we have defined a variable here, alpha, and the question is simply for you to identify alpha in terms of x and y. And your choices here, A is xy, choice B is x prime y prime, choice C is x prime y, and choice D is xy prime. And you see you have 1 on these top 2 lines, x on the 3rd line, y on the 4th line, 0 on the 5th line. Here you have a Toffoli gate, and a Toffoli gate, a Toffoli gate, and a Toffoli gate here. So that concludes the only problem for lecture 26, and good luck.